Our first speaker, Professor Tamer Basar, I'm sure he's well known to all of you. He's been with the University of Illinois Urbana-Champaign since 1981, where he currently is Emeritus Professor of Electrical and Computer Engineering, and he also holds other affiliations in other departments and institutions. He is the member of the U.S. National Academy of Engineering, fellow of IEEE, SIAM, and a past president of IEEE Control Systems Society. He was the founding president of the International Society of Dynamic Games and a past president of the American Automatic Control Council. He has received several awards and recognition over the years, including the IEEE Control System Award, the ISDG Isaac Award, AACC Bellman Award, IFA Quadza Medal, IEEE CSS Bode Lecture Prize, and many others. He has around 1,000 publications in systems, control, communications, optimization, networks, and dynamic games. But you probably know him for his celebrated books on non-cooperative dynamic games and robust control. Today, he's going to tell us about policy optimization for optimal control with guarantees of robustness. And without further ado, I'll let the floor to Professor Tamer Basar.
Thank you. So you can hear me well? Because I'm using this gadget the first time. And probably if someone takes a picture, I don't know how it will look. Well, it's a pleasure to be here, to be invited to this, I would say, the inaugural workshop of the new center, NCCR, and congratulations on this long-term commitment by the Swiss National Science Foundation. It's really a recognition of the not only the past accomplishments of control theory and the role it plays in both the economic development as well as the social infrastructures, as well as Florian has mentioned, the supply chain problems, and definitely feedback is an important thing, and the algorithm design is indeed, I fully agree that it's indeed a control system, feedback control system, and so there's a lot of opportunity moving forward, and I will talk about policy optimization here, which will lead to developing learning algorithms as well, and this is, we are still at the first few sort of epochs of this research, and there's still a lot to be done, and robustness is an issue, a concept that I will be concentrating on. And I should mention that this is mostly based, most of the results here, based on work of my former students, I should say, Kai-Ching Zhang, who is now a postdoc at MIT. He was also at the Simons Institute, and he'll be a faculty member at Maryland this fall. And so this work was done when he was still a student, and also Bin Hu, a colleague of mine at Illinois. So I'll provide a brief introduction to reinforcement learning and policy optimization, and talk a little bit about policy optimization for control design. But the bulk of the talk is going to bring in robustness considerations, and the question is, how can you maintain robustness while learning, which is an important thing. And there are different ways of introducing robustness, and one of them is through a mixed design, that is, you optimize H2 norm subject to some H infinity bound, and that brings in robustness. So this is well known to the control community. And the other one is risk-sensitive controller design, and both of them are actually connected with zero-sum games. So those of you who have seen, or it was already mentioned my book on robustness or H-infinity optimal control with Pierre Bernard shows all these connections between H-infinity optimal control and risk-sensitive control and zero-sum games. So when you try to do policy optimization for problems of this type, you run into nonconvexity. So, and in the case of robustness, there is the additional sort of difficulty and challenge, which is lack of coercivity, which does not arise if you are just doing an LQR design. So we have introduced what we call implicit regularization there in order to make sure that while running the algorithm, you maintain the robustness margin throughout. And but not every algorithm, gradient-based algorithm, actually achieves this. And I'm going to argue that only two of them that I'm going to introduce, which are not gradient, which are gradient-based but modified gradient-based. In other words, you are not moving in the direction of the gradient. Those two will ensure this implicit regularization, so therefore you can maintain sort of the robustness throughout the running of the algorithm, and they have either sub or superlinear rates. And this leads to, if I have time, probably I won't, to robust adversarial reinforcement learning, which is a big topic actually in the machine learning literature or community right now, who are not really involved with control at all. And this is one way of actually bringing in or capturing robustness into reinforcement learning, which has been an issue because the simulations did not match the actual implementation. And then I'll talk about some extensions and conclusions. So the reinforcement learning, the RL, as it's known, we know has achieved incredible success in sequential decision-making problems and in continuous control tasks, such as game of Go, video games, and robotics. And most of these successes actually hinge on the algorithmic framework of policy optimization. So this is, you have function approximation, you approximate, and then you can handle large continuous spaces this way. Policy optimization is fairly easy to implement and is scalable to high dimensional control systems. And also it enables the data-driven sample-based search, which is really the topic for future research. There is still a lot to be done in that area. And some of the prominent examples here is reinforced, the actor-critic algorithms, natural policy gradient, which does not always work, deterministic policy gradient, trust region PO, and proximal PO. So let me just briefly talk about the policy optimization for optimal control. As we all know, a general optimal control problem is one where you minimize either a finite or an infinite over a finite or an infinite horizon, a certain cost function. So C is the incremental stage-wise cost, which depends on the state X and the control U. And then you have the state equation, which could in general be a nonlinear. And then you have a certain control set. And so the general approach is you parameterize the control policy. So the control policy is generally some function feedback control. I'm assuming the state feedback in this case. So you parameterize it in terms of some parameter theta, and then you do your optimization over theta. So assuming that the parameterization brings you as close to the optimal solution as possible. Now, if we go to linear quadratic regulator problem, that's when C is quadratic and F is linear, then if there's no hard bounds on the control, then we know that the linear, this is the bread and butter of control theories, the solution is linear. So the parameterization is a natural parameterization. You are not losing anything through parameterization in this case, provided that you pick the right dimension and you have to mapping from X to state to the control. So K is a matrix, so K is your parameter in this case. So the downside of this is that the optimal control is, as we know, is not robust to any perturbations in the system equation. Even if you have small nonlinear perturbations, then you lose robustness. And if there's any noise or disturbance or some modeling precisions, imprecisions, like the A matrix and B matrix in a linear formulation, then you lose optimality, and it could actually drive, even a small imprecision could drive you to very degradation in the performance, which may not be acceptable. And the robust optimal control actually gets around that because you optimize certain objective functional along with a guarantee of robustness. And there are, as I said at the introduction, there are different ways of introducing robustness. One is with sensitive control, and I'll mention this in a bit more detail. The other one is the H-infinity norm constraint from robust control theory. And the other one is worst-case disturbance, that is zero-sum games. All the unknowns or the nonlinearities, say, on a linear system, perturbations can be viewed as controlled by an adversary. All these three ways, actually, there is connection and can be unified through an H2H infinity mixed design. And they're all like with sensitive control is connected to worst-case disturbance with a properly formulated zero-sum game, and bringing H-infinity norm constraint, again, can be viewed as a zero-sum game. So this mixed H2H infinity problem is you minimize the H2 norm subject to an H-infinity norm constraint. Now, the challenge of this policy optimization is that this takes you to a non-convex optimization problem, which is constrained. So even the LQR, if you substitute this, what I had here, as the parameterization, but as I said, this is a parameterization which doesn't lead to any suboptimality, and substitute this into your quadratic cos when C is in quadratic and use the linear state, the J as a function of K becomes a non-convex function. Okay, so even though in the general Hilbert space, if you formulate the problem in a Hilbert space, it's strictly convex. So when you restrict it to a set where the solution actually lies, you lose convexity. So that's an interesting problem. So you look at it from the other angle, that you have a non-convex problem, and as a function of K, but I embed it in a much larger space, and then I get convexity there. So sometimes lifting it to a higher dimensional space simplifies the thing, at least in terms of making sure that you have a solution, unique solution within the set, in the original set that you have started with. But anyway, this non-convexity definitely creates challenges when you do policy optimization, and then you have a constraint. So the risk sensitive, not risk sensitive, but reinforcement learning and many optimal control problems can generally be formulated in this way, where you are minimizing over some finite dimensional parameter space, where the parameter itself lies in a certain set. And so the question is, what sort of constraints are we dealing with? These constraints are sometimes explicit, sometimes implicit. For example, for the linear quadratic regulator, the constraint is essentially a stability constraint if you are doing over an infinite horizon. So that's what your K is. That is the spectral radius of A minus BK has to be less than 1. Okay, we're dealing with a discrete time problem, which is a non-convex constraint set. So the function you are minimizing is non-convex, and you are doing it over a non-convex constraint set. Okay. Now, if you there are other examples of K that we can have. For example, you may want to put some bound on K's norm. You are not allowing for large values of gain. Or there could be safety constraints on the states. You want the state to lie in a certain tube, for example. This is a deterministic problem, so you can assure that. And so these are other types of constraints which makes the problem even more complicated. But now my main sort of topic here is to bring in robustness and see what additional challenges bringing in robustness would produce. And so beyond stability, so you are definitely interested in stability, but you also want robustness. So this is quite well known to this community, of course. What the H-infinity optimal control does is you have a plant, and then you have some perturbation around that plant, and that could be nonlinear. And then you are designing a certain controller, and you look at the sort of transfer function from W to Z. So this is your G, and this is your delta, and you can, this G delta model covers many robustness considerations in control. For example, if you start with a linear system, you can allow for perturbations around the A and B matrices, delta A, delta B. You can have time-varying parameters. You can have delays, time-varying delays. And even you can have a dynamic uncertainty of unknown model, and the delta would have this. And the critical thing here is that is the small gain theorem, which is due to James, which is that if the H-infinity norm of T is less than gamma, and this uncertainty is less than 1 over gamma, then the G delta system is input-output stable. So if the product of the two is less than 1. And so now going from LQR to this robustness, bringing in additional robustness constraints, in addition to the stability, what we want is the H-infinity norm of this transfer function to be less than gamma. Okay, so we want to. So this is your constraint set, which will assure some level of stability. So as gamma goes to infinity, of course, then you are relaxing that second constraint, and this is the stability region of the LQR. So the open question, which I alluded to at the beginning, is how can we enforce or maintain robust stability in policy optimization and using reinforcement learning methods. And do we have any global convergence guarantees, given that we have a non-convex problem over a non-convex set? And what are the rates of convergence for this? So all these are answered for this class of problems in our work. So our results actually apply to both continuous time and discrete time, but I'm going to talk about discrete time only. And this paper, which I had shared with you earlier, which will appear in the SIAM Journal on Control, covers both continuous time and discrete time. So what in the continuous time you have your transfer function given in this form, in the discrete time in this form given the Z transform, and the H2. So this is all known. That the H-infinity norm can be expressed, it's from L2 to L2 or small L2 to small L2. This is in continuous time and this is in discrete time. But this is not important. As I said, I'm going to focus on the discrete time setting. So this is the problem that we are interested in. The JK actually can be upper bounded. The JK that I have here, which is a sort of a implementable expression for a given gain K, and is an upper bound on the H2 norm, as shown by Bernstein and Haddad, and so on. And so the problem boils down to, as a function, if you substitute in K, then it's given in this form, or in this form, equivalent. And I will more concentrate on this form because this is what arises in risk-sensitive control as well. And in this case, the PK solves a Riccati equation given K. Okay, so, and with A tilde here is A minus BK, the feedback matrix. So this is the classical formulation of optimal control with robustness considerations. Now, coming to the connection with risk-sensitive control, which is the linear exponential quadratic Gaussian problem, and this was introduced by Jacobson in 1973. And now you are dealing with a stochastic system and discrete time. There is a continuous time counterpart as well, where the W is the stochastic noise, independent from stage to stage, and you can view it as white noise with covariance W. And the initial state is zero mean and covariance x0. And so the thing with the LEQG problem is that you have the standard quadratic cost over a time horizon of length t. You multiply it by some what's called the risk sensitivity parameter. Beta is positive, and beta over 2 just for scaling purposes. But now instead of taking the expectation of this quantity, which would be the LQG problem, you first exponentiate it and then take the expected value. And then you can take the log. This is the monotonic transformation, doesn't make any difference, just to bring it down to the same sort of a level as the original problem, and then you multiply it by 2 over beta. Again, these are just scaling parameters. And for the infinite horizon problem, of course, you divide by the length of the horizon and take the limb sup. So what this does is essentially when you exponentiate a stochastic, this is a stochastic quantity. When you exponentiate a stochastic quantity, of course, this is not a linear transformation, and it puts more weight on unfavorable paths, sample paths, or values of this quantity, and less weight on the favorable path. So therefore, this is something that's known in decision theory also, and so you are sort of, it captures a risk-sensitive or risk-averse behavior on the part of an individual. And so, because you are not putting the same weight on the, whereas the risk-neutral version, which is the LQG, puts equal weight on all sample paths. And beta is the risk sensitivity parameter, and if beta is very, you cannot afford for beta to be very large, because then you are too pessimistic. If you are too pessimistic, then the value would be infinite. And so there is naturally an upper value on beta, which is the same as having a lower value in gamma. In other words, I haven't said this, but those of you who know H infinity optimal control will know that there is a certain threshold for the disturbance attenuation parameter, which is gamma. And let's say gamma star, and you cannot go below that value, because if you go below that value, then the uncertainty or the adversary can drive the system to infinity. Okay, so there is a natural positive value for gamma, and likewise there is a natural positive value of beta, but the relationship is one is the inverse of the other, as I'm going to mention here. Okay, so this captures a pessimistic behavior, And interestingly enough, the two are equivalent, exactly. In other words, the controller that you obtain for this problem by optimizing this, and there is a unique actual control, provided that beta is not too large, is the same as the control that you obtain from here. So again, summarizing, there exists a certain beta star such that for each beta less than beta star, the minimum of J exists. And if it's larger than beta star, it doesn't exist. If it's infinite, it's unbounded. And the LEQG admits a unique optimal control, which is linear in the state. Okay, and if I pick Q here to be C transpose C, note that C was the output of the system in the H infinity context. And if I pick W to be D times D transpose, then the control is the same in both cases. So there is an equivalence between the two. And the LEQG feasible set is given by this, exactly. So as I indicated, there is a relationship between gamma and beta, and the inverse relationship, and gamma is replaced by 1 over square root of beta in that case. So this is your constraint set. So if you solve one problem, if I solve this one, then I would be solving the LEQG problem as well, and vice versa. So for the LEQG, it's again suffices to search over LTI controllers. That is, you minimize over K this quantity. Okay, I substituted in KX in place of U. Okay, so in this case you have the modified Bellman equation, and which is given in this form, and the question is, what is do we have a closed form expression for this? Because if I want to use gradient iteration, gradient-based iteration, or some modified version of that, then I need the cost function, and indeed the cost is given by this, and which is exactly the same one that I had earlier. And so this is, if you come up with a K such that this generalized algebraic Riccati equation admits a solution which is non-negative definite, that's stabilizing, that is, in this case, this is the stability condition, and satisfies another condition, which places a restriction on beta, then J has this form. So other models, if this covers maximum entropy, H infinity control of Glover and Doyle, and as well as the zero-sum dynamic games. So let me say a little bit about zero-sum dynamic games. So you have now the X0 is initial state is distributed according to some distribution, doesn't have to be Gaussian. And then you have the standard quadratic cost, but then you additionally have a soft constraint on some V. And the V is the disturbance, so which enters into your system, but it's a deterministic disturbance. So what you are doing is you model, as I indicated, you can allow in H infinity optimal control perturbations in A, perturbations in B, and even nonlinear perturbations in the state equation. They can all be captured by this V sub t. And so what you want is you say this is being controlled by an adversary, and I want to minimize J or infimize over U, and then maximize or supremize over V. So the inf sup is what we are interested in, and that's a worst case design. And so there is a strong connection again to LEQG, where beta is gamma to the minus 1 over gamma squared. And the optimal control policies are equivalent, but here you have a second player, of course. You are looking for a policy for U, that's the control, as well as the adversary input, which is V. And one can show that the saddle point solution or Nash equilibrium for this exists, provided that you have this condition on gamma. Gamma should not be too small, or beta should not be too large. And so there is a direct connection between these two. And the difference is that in the LEQG problem, there is a single input, there is a single variable controller that you are optimizing over, whereas in the game problem, you have a pair. You have the minimizer as well as the maximizer. And one can show that the maximizer is also linear in X. Okay, so now as gamma goes to infinity, and here you have the nice interpretation that if the weighting on the adversary is too high, and note that means that you are relaxing the constraint, the H infinity norm, so that's the two are equivalent, and then you have the LQR, the adversary or the disturbance or the unknown nonlinearities cannot affect the linear solution. And so you have the constraint is just the stability. Okay, so now the question is, what about what sort of algorithms do we have to solve this problem? Okay, and so again, I want to minimize J, where it's given in this form, which is the same for LEQG, as well as it's an upper bound for the mixed H2 H infinity, where P solves this thing. Now, I indicated that LQR is also a non-convex optimization problem, but it has some appealing properties, which is that if your iteration in K gets closer to the boundary of the stability region, your cost will go to infinity, so you will never reach the boundary because of that. Whereas with the H2 H infinity control, you can easily reach the boundary and violate the H infinity constraint. So that's the difference between the two, even though both are non-convex. So we say this lacks coercivity, whereas this one has coercivity, which makes development of algorithms like the policy gradient and so on much more things. So H2 H infinity mixed design is non-convex and non-coercive. That's as K reaches the boundary constraint set. JK does not necessarily. So if you are looking at the cost function itself, it doesn't give you any indication, it doesn't signal to you whether you are violating the constraint or not. So that's the main challenge. LQR is JK descent cannot ensure feasibility in contrast to LQR. So the question is, what in the paper we addressed, we said, how can we enforce this during learning? What sort of algorithms should we have in order to avoid situations of this type? So in other words, what we want is we want to have algorithms where if you start with a K within the constraint region, and if you move to the next iterate, then you still remain in the constraint region. So there are three possibilities for these problems. One is policy gradient, which directly works on the gradient of J with respect to K, and which can be explicitly computed in this way. And there is the natural policy gradient where you post-multiply the gradient by some lambda, which is the unique solution to a Lyapunov equation. And then there is the Gauss-Newton, where you again have the same post-multiplication, but also have a pre-multiplication. So there are connections between natural policy gradient and policy gradient over Riemannian manifold, and Gauss-Newton, when you pick the step size to be equal to 1/2, it reduces the policy iteration for LQ games. Now, so we are looking for, again, regularization iterates. Now, one way of making sure that you stay in a stable set, that question may come up, in the constraint set is you do a projection onto the constraint set if you violate it. But the constraint set in this case is non-convex, so you cannot do that. So what we are able to show is that the policy gradient violates this constraint, this coercivity, but natural policy gradient and Gauss-Newton methods implicitly regularize the iterates, provided that you have the right step sizes, and thus they preserve robust stability automatically. Okay, so for the discrete time, so for Gauss-Newton, eta has to be less than or equal to 1/2, and natural policy gradient, eta has to be less than or equal to this quantity. You may say it depends on the solution itself. No, it doesn't, because this is the K0 is an initial condition that you pick, and I'm assuming that initially you can pick a K0 so that you are within that constraint region. Okay, so that's correspondent. So if you do it this way, then if you at any step of the algorithm, if you are in the constraint set, then the next iterate also remains in the constraint set. So the message here is that the general descent directions of J do not work, but certain directions do. And the proof, I'm not going to go over the proof. The paper has that. It uses bounded real lemma. I'm going very quickly, and then some Riccati inequalities and some LMI techniques. And so let me... Now the next question I had asked is global convergence. And so this theorem says that if you start within the constraint set, and if K0 is in norm is less than infinity, and you have some controllability conditions, which you would need, at the stationary point K, then under these step size choices I had earlier, both Gauss-Newton and natural policy gradient converge to the global optimum, and the convergence rate is 1/n. And the controllability assumption is needed for the H2H infinity or mixed H2H infinity problem, but it's automatically satisfied for LEQG. So if I had to put down a counterpart of this for LEQG, then there is absolutely no condition given the formulation. And the LQR problem was, there's a fairly recent paper, ICML paper by Fazal, Gere, Kakade, and Mesbari, and there is a global gradient domination there. But here the challenge is that we don't have global gradient domination. And so for that reason, it's only 1/n rate globally. Now you have faster local rates, superlinear rates, around the optimum if you start close enough. So some simulations here indicate that you can see the average gradient norm squared, and then there is a big drop, and then fairly close, so this is 10 to the minus 30. And the difference between JK and JK star, again, it drops very fast. And the H infinity norm itself, this is the desired one level, and then you stay below it for both algorithms, and the step sizes are picked as such. And if you start near the boundary of delta K, now here you can see that the red one is the gradient-based one. It violates the constraint. So you want to stay under this gamma, but then it violates it. So this is an indication that the policy gradient does not work. So what's the implication for this, for zero-sum games? I think I'm running. How much time do I have?
3 minutes.
Sorry?
3 minutes.
3 minutes, okay. So for multi-agent reinforcement learning, the zero-sum LQ games, so as I indicated, there is an equivalence as far as the theory goes between the LEQG and mix H2H infinity and zero-sum games. But the question is, does this equivalence carry over to policy optimization? Now, this is not an immediate result because if I have to apply policy optimization to a zero-sum game, now I have two parameterizations to work with. One is the control parameterization. The other one is the parameterization for the maximizer's control. So K and L. And the question, so we're looking for minimizing with respect to K and maximizing with respect to L. Now, when you have two variables like this, minimizing and maximizing, the order in which you do this, or whether you do it in parallel, where the minimizer and maximizer takes turns, or you have two different loops, outer loop and inner loop, where one of them actually, the outer loop, you have a K, and then you wait until some convergence or almost convergence takes place on the inner loop, and then you come back and update on K. So which one would work in this case? And it turns out that actually taking turns is not the right way to do it. You have to introduce outer loop and inner loop optimization. So for fixed K, Swiss precision, for fixed K, you have the outer, which is the outer loop. You fix a K and maximize over L, which is the inner loop. And then after you are confident that you are closer to the maximum value, and then you update K. So that's what works. So that's what's discussed in the paper. This is a non-convex, non-concave in KL. Now you have two parameters, of course. So here is, for example, what could happen. And you think that things are converging. This is when they take turns. And this is the stability. You are looking at the stability of the feedback system with the minus BK minus CL. And then it all of a sudden, it drives to infinity. You lose the stability region here as well. So these things, so this would be, you might be thinking that I'm doing extremely well here, but this is the dangerous zone because you jump off the infinity. So whereas if you do this inner and outer loop, then one can prove that we do not have this type of behavior showing up. So one can show convergence and so on. I mean, with fixed L, of course, the going over K is what I already discussed, the outer loop stability. And the important thing is how to initialize both the K and the L0. And we have ways of doing that. I'm going to skip from here. So you have the going from here to model free H2H infinity control design. You have to sample the trajectories. And then, but in the case of zero-sum games, you have to build a virtual adversary there, and then do both at the same time within this double loop framework. And then we have another paper that discusses this model-free policy optimization for this. Okay, so concluding remarks is. We now have a much better theoretical understanding of policy-based methods in learning for robust control and what sort of challenges this brings, how they can be addressed. And I discussed global convergence here. Implicit regularization is an important concept, new concept that is brought in, which is very much algorithm dependent. And it is important that while you are learning things, whether policy optimization or in a model-free setting, that you maintain the robust stability properties. And so linear quadratic zero-sum dynamic games I have discussed. So we have some ongoing and future work and on sample complexity. For example, the zeroth order methods fail in this case. And mixed design for other types of dynamical systems. Policy optimization for H-infinity optimal control. I haven't discussed that. In other words, you want to minimize the H-infinity norm, but that's a non-smooth optimization problem. I'm not sure whether that's important, but I just wanted to point out. And at the higher level is how can we enforce safety, robustness constraints on the fly in policy-based model-free RL in general. So I hope it was a very tall order that Florian gave us, and I hope I have addressed some of those concerns, but there is still a long way to go. Thank you.
Thank you, Professor Basar. The floor is open for questions. There should be Frederick with the mic there.
Thanks very much, Tamer. It was an excellent talk, and I love the summary of H-infinity from this point of view. So my question is really for the, until we've designed and optimized the very best methods, there are a lot of poorer methods out there. And so if I was to advise a practitioner looking to do an H-infinity constrained design, is it possible to use the flexibility in modeling uncertainty to model some error in K and recover coercivity from the wider variety of possible algorithms?
Oh, you mean well, if you have model uncertainty, then definitely you can lump it into the H-infinity constraint. But if you have K, this is a global, we have global convergence. So if you have small sort of inaccuracies in the computation of K in the iterations, that's fine. That's definitely not going to create a problem because of our proof techniques and so on. Yeah.
Okay, thanks very much.
Other questions? I invite again the online audience to just type questions in the chat, if any. John, there's one.
You can always send me the questions later also.
So if I if I have time, just a quick one. On the connection to when you turn it into a game in the end and you have this alternating K and L,
right.
I imagine this is some kind of timescale separation thing. So the bound you get is you have to get all the way to convergence on the L, or take a few steps on the L and then go back. So how is that formulated?
We have a bound on the number of iterations that you have to do based on the step sizes for the maximizers. But it is indeed a time scale separation that is between whenever you have an inner loop and outer loop, ideally you would like for each K minimizers control gain to have an accurate maximization on the part of the adversary. But if you don't have an accurate, we show that error, the concern would be if that propagates and then drives you outside. But it doesn't. So the error that you make remains as a sort of within some bounds. And so therefore, yes, you can afford not going all the way to the optimum, but you have to be within a certain range of the optimum.
This is based on some contraction rate that you can bound the number of steps.
Right.
Okay.
Yeah.
We have another question there.
I'm going to take advantage that I'm close to the microphone here. So you mentioned that this constraint formulation is equivalent in some sense to the LQ zero-sum game setting, right? Dynamic game. But the way that we optimize them or solve them can be very different. And some of them, like say, for instance, policy gradient converge for constraint optimization, but this gradient descent ascent might not really work for the min-max, the zero-sum gain setting. So does this, suggest that constraint optimization formulation is better than minimax zero-sum gain formulation? Just
from the point of view of learning, yes. I mean, when I say that the two are equivalent, or all three are equivalent, I meant at the level of the theory of existence and uniqueness, when you have the full model. But when if you do policy optimization, then you are bringing something on the top of that, and an iterative algorithm and so on, and you lose the equivalence between the two, because in one case you are just iterating on K only, in the other case you are iterating on both K and L. So there you have the two diverge in a sense in terms of this additional requirement that you bring on the problem, that is using policy optimization you want to reach convergence. Because there is in one case you are bringing in another active player into the game. But LEQG does not, that's a stochastic control problem. And that one is, again, a simple iteration. And there you do not have, it's the noise is actually playing the role of an adversary there. And the fact that you are dealing with an exponentiated cost brings in risk sensitivity, so it's putting the right weights on different sample paths.
Yeah, I see.
And so that essentially automatically plays the role of an adversary, but it's already built into the system itself.
Right. Thank you very much. Yeah.
We ran out of time, so we need to close this Q&A here. Let's thank the professor once again.